A flagship carries weight beyond its weapons. The ship designated as the Strike Group Commander's platform is not simply the largest or the most capable vessel in the formation. It is the node through which every tactical decision is coordinated, every communication is filtered, and every resource allocation for the group is managed. Removing it from the operational picture does not merely reduce the group's combat power by one ship. It removes the architecture that integrates all the other ships into a coherent whole. This is the calculation that shapes the threat assessment for flagship operations, and it is the calculation that the Iranian strike planners had been working with for 3 weeks. Before the night of 2:33 a.m., USS Arleigh Burke was operating as the strike group flagship in the northern Red Sea, 62 miles south of the Suez Canal transit lane. The designation had been publicized not through any intelligence failure, but through the deliberate visible operations that a flagship conducting its coordination function necessarily performs. The volume of communication traffic, the pattern of helicopter movements between the Burke and the carrier, the specific electronic emission signature of a combat direction system running at flagship operating tempo. All of these were observable to the persistent surveillance architecture that Iranian intelligence had built into the Red Sea corridor over the preceding decade. The Iranian analysts who had been tracking the strike group's operations did not need a penetrating intelligence capability to identify the flagship. They needed patience and the ability to read the pattern that the flag's presence wrote across the electromagnetic environment every day. It was on station. At 2:33 a.m., the Arleigh Burke's EW suite detected a low probability of intercept radar emission from a bearing northwest, a radar operating at power levels and in frequency bands designed specifically to reduce the chance of detection by a surface ship's electronic warfare system. Not to eliminate the chance, to reduce it. The difference is operationally significant. An emission designed to be undetectable is never used, because the constraint it places on the using platform renders the using platform operationally blind. An emission designed to be hard to detect is used because it provides the platform with targeting information while keeping the detection risk at an acceptable level. The EW supervisor who identified the emission at 2:33:14 a.m. had been working that specific frequency band for 6 hours, based on a standing order from the operations officer, who had read the updated intelligence assessment on the Quaher 3133 3 days earlier, and had added its assessed emission profile to the EW system's priority watch list. The Quaher 313 is a subject of debate in the Western defense analytical community. Its existence is documented. Its public demonstrations have been assessed by external analysts as showing an airframe that may or may not achieve the performance characteristics its developers have claimed. The debate focuses on its aerodynamic properties, its engine performance, and whether its external geometry is consistent with a genuinely low observable design or a demonstrator that presents a low observable appearance without achieving low observable radar cross-section across the frequency bands that matter operationally. The debate is genuine, and the uncertainty is real. What the updated intelligence assessment had added to that debate was a single data point from a collection source whose provenance the analysis cell had rated as reliable. The Quaher 313 program had recently completed an integration test with a domestically produced cruise missile variant, a weapon derived from the Ya Ali air-to-surface missile family, extended in range, equipped with a terminal seeker optimized for ship targets, and designed to be carried internally in a configuration that reduced the radar cross-section penalty of an external weapons load. The EW supervisor called the contact at 2:33:19 a.m., 5 seconds after the initial emission detection. Not a confident characterization, a possible with a specific frequency match to the assessed emission profile that gave the possible more weight than the word alone conveyed. The TAO elevated the watch posture at 2:33:21 a.m., In the 60 seconds that followed, the SPY-1D completed 7 full scan cycles. On the 6th scan, the fire control system resolved a contact at 54 kilometers bearing northwest. A contact that was present on one scan and absent on the next in the pattern characteristic of a low-observable airframe that was visible to the radar on some of its aspect angles and not others. The contact had a velocity of approximately 800 kilometers per hour. Not a surface contact, an aircraft. At 54 kilometers, the Arleigh Burke had a detection that was not yet sufficient for a fire control quality track. The TAO had a decision to make in the time available before the contact closed from 54 kilometers to a range where its weapons could be employed. He had an LPI radar emission that matched the Quahair 313 profile. He had an intermittent aircraft contact at 54 kilometers. He had the standing intelligence assessment that assessed the Quahair 313's cruise missile deployment as recently confirmed. He did not have a weapons employment radar from the aircraft. No fire control radar, no missile seeker activation, no electromagnetic indicator of imminent weapons release. Under the rules of engagement, the characterization of the contact as a threat requiring immediate defensive action required evidence of hostile act or hostile intent. An intermittent aircraft contact at 54 kilometers on a night when the intelligence assessment said the Quahair 313 was potentially operational in the maritime strike role was a case for the rules of engagement that the JAG had not written a clear answer to. He requested engagement authority from the Admiral's watch team at 2:33:48 a.m. The request was received and the authority question was being processed when the cruise missile launch occurred. The Ya Ali-derived launched at 2:34:03 a.m. The launch generated a thermal signature that the infrared sensor array resolved instantly and unambiguously, a jet engine at ignition power accelerating away from the aircraft, transitioning to cruise speed in the profile of an air-launched weapon in its post-launch acceleration phase. The fire control system updated the threat track from possible aircraft to confirmed weapons employment at 2:34:04 a.m. 1 second from launch to confirmation. The engagement authority arrived at 2:34:05 a.m. 2 seconds after the launch, 1 second after the confirmation. The SM-2 fired at 2:34:06 a.m. The cruise missile was at 41 kilometers and closing. At its cruise speed, the time to impact was approximately 160 seconds. Sufficient time for a well-executed intercept sequence if the fire control quality track on the weapon was stable. The track was not stable. The Ya Ali-derived, like the aircraft that had launched it, had been designed to reduce its radar cross-section in the aspects most critical to the engagement geometry. The nose-on and near nose-on aspects that a defending ship's radar sees when the weapon is inbound on a direct approach. The fire control system's track quality degraded as the weapon closed from 41 to 30 kilometers. As the aspect angle moved from the launch visible side aspect toward the attack profile nose-on geometry, the SM-2 intercept was computed against a track that was intermittent. In the same way the launching aircraft had been intermittent. The weapon flew through the volume of space where the fire control solution said the cruise missile was. The cruise missile was not there. The track's position uncertainty had been large enough that the intercept solution had placed the SM-2 at the wrong point in the space the missile was transiting. The miss was not narrow. It was 40 meters, wide enough to be unambiguous, wide enough that the post-engagement analysis would find no evidence of warhead detonation in proximity to the target. The second SM-2 was already in the air before the first had missed. The TAO had fired in pairs, giving the second missile the updated track correction that the first weapon's miss would provide. The updated solution was better. The second SM-2 detonated within 15 meters of the cruise missile's center line at 2:34:41 a.m. The fragmentation pattern from the warhead reached the cruise missile's airframe and produced damage to the propulsion system and the guidance electronics. Not a kill, a disruption. The cruise missile's speed dropped, its approach trajectory shifted downward by 8 degrees. and its guidance system transitioned from its primary seeker mode to its inertial backup. The same failure mode that the College Fars had demonstrated against the Cole, in which the weapon's last computed target position became the guidance reference, and the weapon's subsequent trajectory was driven by inertial calculation rather than active seeker update. The inertial backup had a position error that the disrupted guidance system could not correct. The error was 17 meters in the horizontal dimension and 6 meters in the vertical. Small errors in absolute terms, significant errors in the geometry of a weapon that had been targeted at the ship's bridge structure and was now tracking the last computed position of that structure with a 6-meter vertical error in the downward direction. The Phalanx fired at 2:34:58 a.m. The cruise missile was at 900 meters. The CIWS burst impacted the airframe and disrupted its remaining aerodynamic stability. The missile pitched further downward in its final 300 meters of flight. It struck the ship at 2:35:01 a.m. at a point 12 meters below the intended bridge impact. At the level of the main deck on the starboard forward hull at frame 29, the warhead detonated against the main deck hull plating at 2:35:01 a.m. Frame 29 on the Arleigh Burke starboard bow was, in the ship's as-built drawings, the location of the forward steering gear access trunk, the passageway that connected the main deck to the below-deck space housing the forward steering actuator assembly. The steering actuator was not in the primary blast path. The access trunk framing was. The detonation energy that propagated through the main deck plating and into the access trunk transferred its remaining force into the structural members of the trunk at the frame junction, and those structural members, absorbing the energy in the way that structural steel absorbs sudden loads, transmitted a portion of it downward through the deck to the forward steering actuator mounting bolts. 2 of the 4 mounting bolts sheared. The forward steering actuator shifted on its remaining 2 mounts by 11 millimeters. 11 millimeters at the actuator became a measurable angular error at the rudder. A rudder that was now deflected 4 degrees from the position the helm was commanding, producing a persistent drift to starboard that the helmsman felt as a heaviness in the wheel that was not present 30 seconds before. The helmsman reported the steering anomaly at 2:35:09 a.m., 8 seconds after the detonation. The officer of the deck ordered the steering shifted to the secondary steering system at 2:35:11 a.m. The secondary steering system on an Arleigh Burke runs through a separate hydraulic circuit connected to a secondary actuator positioned aft of the primary. The system shift was completed at 2:35:19 a.m. The secondary system responded normally. The rudder came back to the commanded position. Steering control was maintained, but the primary actuator, still connected to the rudder through its 2 remaining mounting bolts, now misaligned by 11 millimeters, was producing a mechanical interference with the secondary actuator's control of the rudder. The secondary system had to work harder to hold the rudder at its commanded angle because the misaligned primary actuator was applying a resistance load at the rudder connection point. The hydraulic pressure in the secondary circuit climbed above its normal operating range at 2:35:31 a.m., triggering a pressure relief that partially compensated but did not eliminate the interference. The ship was steerable. The steering system was degraded. If the pressure anomaly in the secondary circuit progressed, the ship would eventually lose steering authority from the secondary system as well. And at that point, the only remaining option was the emergency electric tiller, a manual steering mode that provided limited rudder control at reduced speed, and that was not compatible with the tactical maneuvering requirements of a flagship in an active engagement environment. The engineering officer reached the forward steering gear room at 2:36:02 a.m., 1 minute and 1 second after the detonation. He assessed the actuator mounting damage visually and confirmed the displacement. The 2 remaining mounting bolts were intact and were holding the actuator in its displaced position. The repair required removing the 2 sheared bolt remnants from their holes, installing replacement bolts from the steering gear emergency repair kit, and retorquing all 4 bolts to their specification while maintaining the actuator in its correct alignment. A task made complicated by the fact that the actuator had to remain connected to the rudder linkage during the repair, because disconnecting it would have transferred all steering to the emergency tiller mode that the current operational situation could not accommodate. The repair required alignment tooling that the emergency kit provided in a reduced form. Not the precision alignment jig that the procedure in the maintenance manual specified, but a flat bar alignment guide that could be positioned against the actuator housing and the mounting plate to verify that the replacement bolts were drawing the actuator back to its correct position, rather than drawing it to the displaced position that the sheared bolt stubs had held it in. The alignment was the critical step. Without it, replacing the bolt simply locked the actuator in the wrong position. The machinist's mate working the repair used the flat bar guide at 2:37:41 a.m., confirming the alignment before the first replacement bolt was torqued, and completed the 4-bolt replacement at 2:39:54 a.m. The forward steering actuator was returned to full alignment and full function at 2:39:54 a.m., 4 minutes and 53 seconds after the detonation. The hydraulic pressure anomaly in the secondary circuit resolved immediately as the mechanical interference was removed. The steering system was restored to full primary operation. The hull damage at frame 29 was the other immediate casualty from the detonation. The main deck plating had been breached, not flooded because the breach was at main deck level rather than below the waterline, but structurally compromised in a section that was adjacent to the forward VLS battery's structural foundation. The breach did not extend to the VLS foundation. The structural survey that the DC team conducted at 2:41 a.m. confirmed that the blast energy had not propagated to the VLS foundation framing. The forward battery was intact. The hull breach required temporary patching. A steel cover plate welded over the opening to restore weather deck integrity and prevent water entry in heavy weather. The ship's welder had the plate cut and tacked in position at 2:51 a.m., and the weld complete at 3:09 a.m. The repair was not a structural restoration. It was a weather seal, adequate for continued operations but requiring dry dock repair before the ship's next scheduled maintenance availability. There was a second threat element that the crew of the Arleigh Burke had not yet fully characterized while the steering repair and hull patching were in progress. At 2:34:11 a.m., 8 seconds after the Ya Ali-derivative's launch, the EW system had detected a second category of emission from a bearing southeast at a range consistent with a position on the Yemeni coastline. The emission was in the frequency band associated with a drone relay system. Not the targeting radar of a weapon, not the fire control system of a launching platform, but the communication relay architecture of an airborne relay drone that was routing data between a ground-based observation post and a receiving station. The emission pattern was consistent with a targeting data relay, the kind of real-time position transmission that a shore-based observer would use to correct the fire of a coastal missile battery against a moving ship. The shore-based coastal battery had not yet fired. It was receiving position updates. It was computing a firing solution. And the Arleigh Burke, with a primary actuator under repair and a hull breach being patched, was not maneuvering in the unpredictable pattern that would have complicated a firing solution built from real-time relay data. The TAO reported the relay drone emission to the Flagwatch team at 2:35:41 a.m. The Admiral's decision arrived at 2:36:08 a.m. The P-8 Poseidon on the Northern Barrier Patrol was vectored to the relay drone's estimated position. The P-8 reached the datum at 2:41 a.m. and identified the relay drone, a small, propeller-driven quadcopter-class vehicle operating at altitude, its relay transmitter creating a clear, stable emission source that the P-8's sensors resolved without difficulty. The drone was neutralized by the P-8's onboard electronic attack system at 2:42:14 a.m. The relay link to the coastal battery was severed. Without real-time targeting updates, the coastal battery's firing solution degraded from an operational standard to a dead reckoning extrapolation. The battery did not fire. The tactical logic of waiting for updated data rather than committing to a degraded solution was sound. A coastal battery that fires with a dead reckoning solution against a maneuvering ship at night in the Red Sea is more likely to reveal its position than to achieve a hull strike, and a revealed position in the current operational environment had predictable consequences. The coastal battery did not fire. At 3:12 a.m., the Arleigh Burke's damage assessment was complete and transmitted to the fleet commander. The report documented the forward actuator repair, the hull breach weather seal, the forward VLS battery status, the Ya Ali-derived engagement results, and the relay drone neutralization. It documented the ship's current operational status as fully functional in all combat systems, fully mobile, and fully capable of continuing flagship operations. The fleet commander read the report. The Burke remained the flagship. Here are the numbers when the assessment is transmitted and the watch continues. 6 hours, the EW supervisor monitored the Quahair 313 emission profile before detection. 2:33:14 a.m. First emission detection. 2 seconds from cruise missile launch to confirmed threat classification. 40 meters, SM-2 miss distance against the low-observable approach profile. 15 meters. Second SM-2 miss distance after guidance disruption. 12 meters below intended bridge impact. The Phalanx deflection that changed the hit point. 11 millimeters. Forward actuator displacement from 2 sheared mounting bolts. 4 minutes 53 seconds from detonation to steering fully restored. 8 seconds from detonation to helmsman steering anomaly report. 1 relay drone neutralized by P-8 at 2:42:14 a.m. 0 fatal outcomes among the crew. The flagship held its position. The Iranian strike architects had planned against the flagship's function, not just its hull. A strike that degraded the Arleigh Burke's ability to coordinate the strike group. Its communications, its command spaces, its steering, was more operationally valuable than a strike that produced hull damage without disrupting the coordination function. The bridge impact that the Ya Ali-derivative's original trajectory had been targeted at would have achieved exactly this. A hit at command deck level that disrupted the flag watch team and potentially the command architecture at the moment it was most needed. The Phalanx deflection that moved the impact point 12 meters downward was the margin between a strike that achieved its operational objective and a strike that produced a 4-minute 53-second steering repair. The EW supervisor who had added the Quahair 313 emission profile to the priority watch list 6 hours before the engagement had not known he was going to detect the aircraft. He had added the profile because the intelligence assessment had said the capability was possible, and because adding a frequency entry to a watch list costs nothing and costs everything to omit. The 5-second warning that the detection provided, the 5 seconds between 2:33:14 a.m. and 2:33:19 a.m. when he called the contact, was the time that elevated the watch posture before the launch that had the SM-2 committed in 6 seconds rather than the 20 it would have taken from an unprepared posture, that reduced the cruise missile's closing time before the first intercept from the full 160 seconds to the shorter window that gave the second SM-2 its degraded but functional guidance disruption. 5 seconds built from 6 hours of attention. That is what the flagship's survival was built from. The Red Sea does not acknowledge the watch that never sleeps on the ships that cross it. It does not need to. The watch keeps itself